So, good morning, everyone, officially, and welcome to this Plasmonic Forum, which is special Plasmonics Forum. Those who attended very first Plasmonic Forum back in 2015, they might remember that first Plasmonic Forum was actually final project meeting for active Plasmonic program grant. And it was so popular and so good that we decided to keep Plasmonics Forum every year. And over the last 5 years, we had lots of interesting talks and lots of interesting discussions. And luckily, after active Plasmonic program grant in 2015, we were awarded Reactive Plasmonics program grant. So Plasmonic Forum was really a venue where we can advertise this project and present its achievements. But this year, Plasmonics Forum again is very special one because we are coming to the end of Reactive Plasmonic program grant. And this Plasmonic Forum is essentially, again, to present achievements of our program grant to the world. So this would be first part of Plasmonic Forum in the morning, and then in the afternoon, traditionally, we will have external speakers and external posters, and most importantly, roundtable discussion, where we can hope to hear views from all participants about where nanophotonics, photonics, plasmonics, metamaterials, where all this field go and what expect us in the future. So just a few words about reactive plasmonics. So reactive plasmonics is program grant, so it means long-term investment from UKRI and in particular from EPSRC. So Reactive Plasmonics officially started on 1st of September 2015, and we had exciting 72 months to do great things, and you will hear some of the results today. Long title for Reactive Plasmonics project is Optical Control of Electronic Processes at Interfaces for Nanoscale Physics, Chemistry, and Metrology. And this collaborative project between Imperial College London and King's College London, as well as we have exciting industrial partners contributing to this project. So what is reactive plasmonics? So plasmonics in general, I don't need to say in this forum what plasmonics is. It is essentially if we have metals have free electrons, and free electrons provide particular optical response with negative epsilon. And because of this, we can excite surface plasma polaritons at the interface of smooth metal films, as well as localized surface plasma if we have nanostructures and nanoparticles. I think there is echo somewhere. Maybe if everyone try to switch off microphones, please. Please. Megan, could you please switch off everyone's microphone, but mine? I will unmute myself. Is it better now? Yes, I think it is. So yes, so this plasmonics as we know it, and we know why plasmonics is so good. Plasmonics is so good because we can couple light to electron motion, to free electron motion, so we can squeeze electric field very close to surface of metal or very close to nanostructure, so field is enhanced. And from this, we can have several interesting properties. For example, we can have field confinement, enhancement. This provides us sensitivity to surroundings. So this is why plasmonics is so good for sensing application. It's so good for enhancement of nonlinearity and many other effects. However, if what is more important, if you combine plasmonic nanostructure with some kind of functional materials, it could be electro-optical material, magneto-optical material, nonlinear material, then plasmonics helps to enhance all these functional properties that are important for photonics and other applications. Yeah? So this is what we started previously in active plasmonics, and how we knew plasmonics kind of until five years ago. So essentially we used this field confinement and enhancement in order to control controlled by surroundings. If we change shape of the nanostructure, or if we change environment, we can control the surface plasmon, we can guide surface plasmon wave in very tiny sizes, etc., etc. However, what will be if we try to do other way around? So if we do it other way around, then we will have reactive plasmonics. And reactive plasmonics is essentially surroundings controlled by surface plasmons. Because when we excite surface plasmons, we excite collective motion of free electrons. These free electrons then can decay into very high energy electrons, or holes. So generally we can call it hot carriers. Although for plasmonics metals in many cases it's hot electrons. And then if we are able to extract these highly energetic carriers from the metal, we can do some beautiful things. For example, we can achieve light detection with semiconductor for photon energies much smaller than band gap of semiconductor, or we can do some chemical reactions or enhanced catalysis when electrons interacts with molecules which are next to metal nanostructure. So essentially it allows us to harvest some of the disadvantages of traditional plasmonics, because we always were complaining that plasmonics is very lossy compared, for example, glass compared to optical fibers. So plasmonic waveguides are lossy, although they are very small but lossy. However, if you want to harvest hot electron effects, the loss is no problem. Loss actually is advantage. So you need to find the balance between lossy and plasmonic properties of materials. So we can control surroundings by surface plasmon by means of enhancing chemical reaction or stimulated chemical reactions, and or use these hot electrons in semiconductors for photo detection. So in order to do this, we need new family of plasmonic materials with appropriate properties. We need to control and pay attention to interface properties if we want to extract these hot electrons efficiently. And as I said already, all these properties leads to important applications like photochemistry, photocatalysis, photodetection, nonlinear optics, etc., etc. So objectives of this program grant were to study new plasmonic materials with control properties and photophysical interactions, to provide investigation of hot electron effects, roughly speaking, to understand hot electron effects. So what are they, how they can be maximized, how can be used most efficiently, and then to study various nanoscale, this hot electron induced thermal and non-thermal effects for application, and then to use this knowledge for application in chemistry, optoelectronics, and nonlinear optics. So the project was structured around these four general themes, looking into new plasmonic materials with properties specifically tailored to enhance hot electron effects, study fundamentals of hot electron effects, study hot electrons and interfaces, because as I said, it is very important, and then look at the applications of these hot electrons. So we had wonderful team with 9 co-investigators, 6 postdocs funded by EPSRC, 1 postdoc funded by project partner, and 8 PhD students funded by the project partner, as well as we had countless affiliated researchers who were attracted to the program because of interest in physics that we were looking at, and they also contributed to this work. We had very strong project partners who contributed in different ways to the program, including advice on developing applications, advice on how to move project in most promising direction. So we are very grateful to all project partners who contributed to this work. Over the last 5 years, very many people worked on a project, and there are still few months standing, continuing until the end of the program in August this summer. But many people already left, and we are very happy how their career developed. So many of them become professors in various universities across the globe, from Argentina to China, and many work as postdocs in some of the leading universities around the world. We are very grateful to all their contribution to the success of the project, as well as we are very grateful to all to those who still continue working on the project in the last months of the program. Well, so over the last 5 years, we published more than 140 articles, and I hope many of you read those articles and like them. So I don't know exactly how many articles were published, because this number changes literally every day, but it's definitely more than 141. In terms of conferences, so generally I would expect this number to be much larger. Unfortunately, impact of COVID had impact on this number. But anyway, we had like more than 100 plenary keynote tutorials, so invited talks, which resulted from the work in this Reactive Plasmonic program grant, and had 2 patent disclosures, which we hope we can commercialize in due course. And many publications attracted interest in general and professional press, and probably you had a chance to read kind of short, simple summary of these articles in various general publications. We contributed to the community, so we contributed to looking at future horizons for photonics research, which was conducted by Photonics Leadership Group and Materials for Energy Transition Roadmap, commissioned by Royce Institute. There were many successes. This just some of the fellowships and awards that members of our team achieved. So it was Royal Society Short Industry Fellowship with Dr. Mazar Nazir, who works with kinetic in terms of looking at application of some of the hydrogen sensors developed in the course of this work. Emiliano Cortes, who was a postdoc on this grant, was awarded ERC starting grant quite some time ago already. And Stefan got a ACS Nano 2020 Lectureship Award. Some of the PhD students also had significant achievement, like Margot Cordova Castro was invited to participate in the Dow Nobel Laureates meeting. And of course, we organized many interesting meetings for communities, in particular Reactive Plasmonics UK Catalysis joint workshop, which was very interesting to join kind of chemistry and catalysis community with reactive plasmonics community, which allowed us actually to develop some new idea, and I hope you can hear about this new idea in due course in the future. And in November 2020, we had Reactive Plasmonic Industry Day, specifically oriented towards our industry partners, which was great success and allowed to highlight kind of more industry, more application-oriented work resulted from reactive plasmonic to industry, not just our industrial partners, but all industry in the UK. And we also organized several meetings, scientific meetings, including Faraday discussion, which was a forum to discuss some of the very, I should say, controversial issues around hot electrons and plasmonics. It was really great discussions. So this some of the highlight what we have done for community during this program grant. So we organized a special issue on hot electron effects, which helped to kind of map the field of plasmonics hot electron at the beginning of the project. Then there was this Faraday discussions when there was really intense discussions related to different issues of hot electrons, and there is essentially proceedings of these Faraday discussions published as a book. So if you're interested, I encourage you to read in particular discussion sessions as well as papers published in this book. Joint workshop with UK Catalysis Hub, and you see here faint the word the opportunity, and indeed during this workshop we found many opportunities to advance this field, and as I said, hopefully we can report on these opportunities next time at the next year London Plasmonic Forum. Industry Day. So during Industry Day, as I said, we focused on particular areas which we thought would be of interest for application, for commercial application, in particular for sensing, catalysis, nanoscale heating. We exhibited some of the effects and applications developed during this project in various forums, including SPIE Photonics Europe Innovation Village, Future Photonics Industry Hub, or Innovate UK Emerging Technologies in Metamaterials. And this you can see in various photographs from this event. So people really were interested to see what actually plasmonics can do for various applications, in particular what hot electrons can do for various applications. We worked together with artists to celebrate International Day of Light, focusing on beauty of plasmonics. I always said that plasmonics is extremely beautiful science. And we went even into pubs. So here one of the co-investigators on the program grant in the pub. What he is doing there? No, he is not doing what you think he is doing in the pub. He is presenting lecture on plasmonics. Not only pub, we went to Parliament as well. And this one reactive plasmonic poster at Stamford, Britain 2018. That time it was still in-person event, and I hope many members of Parliament had the chance to look and discuss what is plasmonic and how it can help UK and UK industry. This just photos from Royal Society summer exhibition for general public. Again, there were lots of interest from general public. And of course, London Plasmonic Forum. So this just snapshot for London Plasmonics Forum for various years, and you see many still young at that time, people, and then getting older and older, but still very happy. And this is from last year. Okay, maybe not everyone so happy, and you cannot see many people on that snapshot, but actually last year online Plasmonic Forum attracted, I think, around more than 250, almost 300 participants all around the world, and we were very happy about this. And here we are in 2021, again online Plasmonics Forum, and we presenting highlights of Reactive Plasmonic Program grant. So initially I thought that I will show you some research highlight with some beautiful pictures, but at the end, for the sake of time, I think I will stop here and we move to main program. And in the main program, we selected 3 talks, which will highlight development of new materials for hot electron application, developments in plasmonic chemistry and photocatalysis, and developments for use of hot electrons in optoelectronics and nonlinear optics. So we will hear with this 3 summary talk, which we try to combine all achievements of the project there. Plus, there are, of course, posters related to our work. I hope you already had the chance to look at those posters and find something interesting there. And during this meeting, you are most welcome to send a message to poster presenters and discuss these posters further during break that we'll have between 12 and 2 p.m. Okay, with this, without further ado, I maybe stop talking about general thing and we look at some science. So I will pass to Stefan Maier to chair the session. Please, Stefan.
Okay, thanks a lot, Anatoly, and welcome also from my end to all of you. So for the next 90 minutes, we have 3 concise highlight talks in the areas of materials, plasmonic chemistry, and hot electrons for optoelectronics. Now, after each talk, there will be the opportunity to ask a few short questions. Now, as you see, the meeting is being recorded. There is always the opportunity for you, if you don't want to end up on the recording at the end, to email Megan or myself, and then we can edit your contribution out. Yeah, so I should just say that properly. Yeah? So please be active and ask us questions. There will also be a roundtable in the afternoon at 3:10. So more questions and more outgoing questions can be asked then. Good, so without further ado, I think we should just start with the first talk. It will be given by Dr. Ryan Bauer from the Materials Department at Imperial, and he will tell us about what we did in our program grant with the discovery for new plasmonic materials.
Good morning, everyone. So as I said, as I've been introduced, I'll be introducing our work on new materials for hot electron applications and some of our work in general on new materials for plasmonic applications. So we've been researching alternative plasmonic materials that allow us to expand the applicability of plasmonic materials and to develop functional devices. So we're interested in overcoming some of the limitations that exist with traditional plasmonic materials. So we've been searching for materials that can help us to overcome these limitations and meet specific criteria. We're interested in materials that are plasmonic, so that display metallic or plasmonic behavior over a large range of wavelengths. We've also recently studied spectral tunability of these alternative plasmonic materials. So looking at tailorable plasma frequency that will allow us to access different wavelengths of operation and therefore target different specific applications. And we're interested in the temperature stability of these materials, particularly when they're patterned on the nanoscale. So we've been researching refractory materials. Also in general, we're interested in materials that are chemically and mechanically stable, biocompatible if applicable, and compatible with CMOS fabrication flows as well, so that we can integrate them into existing device fabrication methods. So we've been developing in the past 5 years our deposition techniques and fabrication methods in order to investigate these thin films and materials. And we've also patterned these thin films and characterized them on the nanoscale. So I'll just highlight some of the highlights and key applications and key materials that we've looked at in the past few years. So firstly, in aiming to expand this materials platform, it's useful to compare and contrast different materials in order to identify which material would be most suited to specific plasmonic applications. So we can see that we've assessed a wide range of materials, including noble metals, refractory metals, transition metal nitrides, and conductive oxides. And they each have their own limitations and advantages, and also wavelengths of operation. So as part of our work in investigating these alternative materials, we developed some quantifiable figures of merit, which would allow us to directly compare these materials and identify which is best for different applications. For example, looking at hot electron generation for solar photovoltaics or photocatalysis, but also for photothermal heating applications. So we deposited thin films of this wide range of materials. We measured their optical properties using spectroscopic ellipsometry and fitted this with a Drude-Lorentz model. And then this data we input and combined with Mie theory in order to identify these quantifiable figures of merit. So I'll just take through a couple of relevant examples here. If we consider hot electron injection and the Schottky barrier figure of merit, we can compared here alternative materials for injection of hot electrons into silicon. So we were looking at materials with a work function of less than 0.8 electron volts, so operating at 1550 nanometers. And we combined, we identified the cross-section of these materials, so the absorption cross-section, in order to allow us to identify the injection efficiency into silicon. So with these materials, we can see that the nitrides and the refractory metals, for example, titanium, are good for N-type Schottky barrier devices. We can also consider solar energy harvesting. So we can see that different materials absorb at different wavelengths of the solar spectrum. So we're comparing here silver, gold, and titanium nitride. And these are nanoparticles that are 80 nanometers in diameter. And again, we can consider their absorption cross-sections in order to identify which material would be most suitable for photocatalytic applications or photovoltaics. So this is all theoretical, so we wanted to confirm this, the materials that we've selected experimentally. So we developed our deposition methods. So for example, we looked at transition metal oxides deposited by pulse laser deposition. We show that these are tunable over optical and near-infrared wavelengths. And this spectral tunability in the screen plasma frequency was possible due to changing the cation in the B site. So if, for example, if we move from SRO to strontium ruthenate to strontium molybdate, we can shift the wavelength of operation. We can also have fine control by controlling the oxygen pressure in the deposition process and changing the oxygen stoichiometry. In these oxide films, we also identified strain-mediated tunability. So by changing the thickness of the film and introducing strain, or by changing the substrate, we can shift the charge carrier concentration and again change the wavelength at which we can operate. So that's useful if we're looking to translate this into plasmonic devices. So we've considered the transition metal oxides. We also considered transition metal nitrides and oxynitrides, where again, we were interested initially in understanding the deposition process. So these films were deposited by reactive magnetron sputtering. And we see that titanium nitride films deposited at high temperature have typical metallic behavior and a Drude response in the real dielectric permittivity. But if we deposit at lower temperatures, we see that we get this double epsilon near zero behavior. And this is potentially interesting for optoelectronic and nonlinear applications. But we wanted to understand why we were seeing this behavior in the first place. And we found that it was due to oxygen incorporation within the thin films. Whether we were introducing oxygen, for example here, or as a residual oxygen partial pressure in the deposition chamber. So by controlling this residual partial pressure and the deposition parameters, for example, temperature, we've shown that we can tune from metallic behavior to double epsilon near zero behavior to fully dielectric behavior in these titanium oxynitride thin films. And the mechanism of this tunability is confirmed using Maxwell-Garnett theory, where we show that by changing the oxygen inclusions within an effective medium, we can shift from this metallic to double epsilon near zero behavior. Depositing at high temperatures, which we need for highly metallic titanium nitride films, is limiting in the practical inclusion of this material in CMOS fabrication process flows, or it also limits us in the patterning methods that we can use. So we aim to deposit at lower temperatures, CMOS compatible temperatures of less than 300 degrees C. And to do this, we collaborated with Sheffield Hallam University and the National High Plasmonics Technology Centre to deposit titanium nitride films using high power impulse magnetron sputtering. And this produces an incredibly dense plasma with highly energetic species, and that allows us to deposit metallic films at these low temperatures. In this work, we also investigated the tunability between niobium nitride and titanium nitride ternary films. So niobium nitride has a plasma frequency in the UV, titanium nitride in the visible, and we showed that if we deposit co-sputtered films, we can tune the plasma frequency between the UV and the visible. We also deposited layered films and found that layered films of titanium nitride and niobium nitride display a blue shift compared to co-sputtered films of the same stoichiometry. So this is potentially interesting and another degree of freedom when it comes to tunability of these films. So that was kind of mostly spectral tunability and understanding the deposition process of these films. But if we're looking to use these materials in practical devices, we're also interested in their temperature stability. So we compared the temperature stability of noble metals, refractory metals, transition metal oxides, and transition metal nitrides in order to identify and map out their operating temperatures, and again, their spectral tunability wavelengths, as we can see in this here. So to do this, we deposited thin films of these materials using electron beam deposition, reactive magnetron sputtering, and pulsed laser deposition. And we completed an annealing study where we heated each of the samples for 1 hour in air from 100 degrees, gradually increasing the temperature in 100-degree increments. And we were waiting to see if there was any significant change in the optical response, in the structural response, or in the surface morphology. And we found that the degradation mechanism for these materials differed depending on the material platform that we were using. For example, gold's response changed dramatically because of surface morphology changes, whereas with titanium nitride and titanium oxynitride, there was little change in the surface morphology, but we did see change in the optical response due to oxidation of the films. And if we look at the refractory metals, for example, tungsten, this is a combination of the two. So we see oxidation of the films and changes in the surface morphology. But as I say, this allowed us to identify which material could practically be used in different applications. But these were thin films, so we're also interested in nano-fabricated devices. So we developed for these alternative material platforms our in-house patterning capabilities. For example, titanium nitride is known to be mechanically robust and stable. So it cannot typically be patterned using existing patterning methods. So we had to develop a patterning method that would allow us to fabricate nano features. And we did this using electron beam lithography and reactive ion etching, a chlorine-based reactive ion etching process. And as you can see here, we can achieve films with minimum feature sizes of 60 nanometers diameter. And we can also deposit arrays of antennas of various shapes using titanium nitride. Once we pattern these thin, small materials and these nano features, we're interested in understanding their temperature stability as well. So we did an annealing study and a temperature stability study using cathode luminescence, where we identified we measured the optical response from individual nanoparticles, annealed them, and assessed the change in the optical response and in the morphology with temperature. And we see that from 200 degrees, there are spectral changes in both gold and titanium nitride, but titanium nitride retained its shape up to 600 degrees. And we supported all of this with modeling. So we did dipole-dipole simulations of the cathode luminescence response of these materials. So in understanding the deposition methods and depositing the material operation wavelengths and their temperature stability, We also want to measure the hot electron dynamics. So if we're interested in using them in hot electron devices, we need to understand what's happening there. So with titanium nitride, again, we use pump probe spectroscopy to measure the hot carrier dynamics in the material here. So in pump probe spectroscopy, we excite with a pump, and then we probe with a time-delayed probe beam by chopping the laser. And that allows us to map out the excitation features here. So we can see the time delay and the lifetime of the hot carriers. So in this experiment, we compared gold with titanium oxynitride, and we were interested in injecting hot electrons into titania. So we made sure to excite these at wavelengths that don't excite any hot carriers in titanium. This is just an animation of the pump probe. So with the titanium nitride, what we found very interesting is that they have these incredibly long hot electron lifetimes. So typically in a metal, we have hot electrons on the lifetimes on the scale of picoseconds, as we see in the gold here, down here. However, with the titania, we have these long lifetimes, up to a nanosecond. And we were aiming to understand why this was occurring. So if we look at it, we compared gold and titania films with titanium nitride, and we see that gold films deposited on titania, so titanium dioxide, also exhibit this long lifetime. So what we're seeing is hot carrier generation in the gold, and then pumping into the titanium. And this is what we attribute to the long lifetimes in titanium oxynitride as well, because we completed SIMS measurements, secondary ion mass spectrometry measurements, which show that the interface in the titanium nitride films is a titanium oxide interface. So that explains the slow response of the titanium oxynitride thin films here. We're currently working on this to understand how the variation in oxygen content within these films can allow us to control these hot electron injection and can be used for practical devices. So we see here, we've changed the oxygen content in these titanium oxynitride films, and we have the best response for 25% titanium oxynitride films. So these will allow us to harvest hot electrons most effectively with this oxygen inclusion. So in addition to top-down fabrication processes and thin film deposition, we're interested in bottom-up fabrication processes and materials as well. So one of these materials is copper sulfide, which is a material that you can fabricate nanocrystals of. So we completed a characterization of the optical properties of these copper sulfide nanocrystals, both experimentally and theoretically, with computational modeling. And what we see is that it is a material that displays natural hyperbolic dispersion. So in the wavelength range of 670 to 1050 nanometers, whereas in the long wavelength range, it displays typical metallic behavior. And these materials, the nanocrystals, have different efficient hot electron ejection and generation possibilities, because they have high field enhancements at different locations based on the shape of the crystal. So we can potentially use these to generate hot electrons from these high field areas. So in addition to natural materials, we're also interested in fabricating metaparticles. So these are materials that aren't found in nature. And the idea behind these metaparticles, which have this kind of onion structure of alternating layers of gold and silica, is that if we put an anisotropic material on top of a plasmonic material, we can access this hyperbolic response, which will allow us to tune the plasma frequency and the dielectric permittivity, and therefore the wavelength at which we can operate over a larger range of wavelengths. Whereas typically, if we coat a material with an isotropic coating, we can change the sensitivity, but we're limited in the refractive index of these materials. Whereas the hyperbolic coatings give us essentially refractive index on demand. So we fabricated these onion-like structures. We can see them in TEM images here of alternating layers. And we see that we have this experimental observation of their optical response. We have this broadband excitation. And we can change the dimensions of the layers in order to tune these modes, these excitation modes, which will allow us to, again, access different wavelengths. So other metamaterials that we fabricated were fabricated using electrodeposition and anodized aluminum oxide, where we deposited nano rods of gold, for example, and then we can change the aspect ratio of these rods. So this is a large-scale fabrication process, which allows us to deposit over wide areas, so we can have a broad area of hot electron enhancement and high field enhancement. And we can shift the optical properties by changing the aspect ratio using argon milling to move from nano rod materials to nano pencil materials and then to nano cones. And we see that this intensity enhancement is concentrated at the apexes, at the tips of the nano cones. And we can tune this by changing the shape of the materials. We can also tune it by changing the spacing of the materials as well. Another large area array that we deposited using this same deposition technique was the split rod metamaterials, where we deposit gold and then a dielectric, and then gold again. So we have these kind of composite rods. And we see from these rods, sorry, I've just closed the screen there. We see from these rods that there's high intensity enhancement within the dielectric material within the rods. So we have these gap plasmon modes. We also have this surface plasmon mode, which works across the whole large area of the material. And then we have the typical surface plasmon polariton modes as well. So I've had a bit of an incident with the slides there, but that's me. So thank you very much for listening. So that's just a brief highlight of some of the materials that we've been working on.
Thanks a lot, Ryan. And let me just add, so on our webpage, reactiveplasmonics.org, you can also take a look at all of these papers and download them via the journals. So we have a few minutes for questions. Does anybody have any question to Ryan or to us in general about the material aspects of what we just presented? You can either unmute yourself and ask, or you can write a question in the chat, which I'm also monitoring. Or you can think about your question and come back for the roundtable discussion. Yeah, Jean-Francois, do you want to?
Yes, actually, I do have a question regarding the luminescence images you've shown at about halfway the presentation. So the gold luminescence was mainly from the terrace of the particle, while the, I think it was titanium nitride was coming from the edge. Do you, is that something consistent, and is that something that could be explained? It seemed that there was a pattern there that I don't understand exactly where it's coming from. Oops, you're on mute.
Ryan, you're still mute.
Yeah. So I'm just going to reshare that slide. I think.
Yeah, I was just going to say, just.
So. Yes, so there is edge effects in the cathodoluminescence in both the gold and the titanium nitride as well. So we see that this kind of increased. Let me just get back to the slide. Increased emission from the edges in both materials there.
Yeah. If I'm not mistaken, the gold had a fairly strong luminescence from the terrace as well. But there we go. Yeah.
My screen sharing just stopped itself. Sorry. So we can see that there is in the gold simulation. Well, we can't quite see, but let me see. Okay. Sorry about this. So this is the slide we're interested in, yeah. So your question was about the simulation here?
Actually, on the left side, you have images. So you see that gold has a fairly strong luminescence from essentially the terrace. while you see the ring or edge effect on titanium nitride. Do you know where it's coming from? What's the rationale behind this?
So we do see some evolution of the kind of higher order modes with increased disk diameter, which might be explaining that there. But with titanium nitride, we have kind of poorer emission, so it's lossier. So we have these generally lower intensity peaks and broader peaks, which might be why we see spectral features in gold that we don't necessarily see in the titanium nitride.
Thank you.
No worries.
Okay, Ryan, one other question from you in the chat from Emily Ringer from Cambridge. Have you considered magnesium?
We haven't worked on magnesium yet. I've seen quite a bit of work about that, but we haven't done any work on that. It'd be interesting to do if you want to do that in the future.
Yeah, that's maybe something to pick up again in the roundtable discussion, where we can maybe have an opportunity to talk about other interesting non-traditional plasmonic materials in this context. So thanks, Emily, for that. And as Anatoly just points out in the chat, feel free also to ask questions as we go along throughout all of the presentations. Yeah, I will make a note of them and then we can efficiently post them. Okay, so thanks for this. Thanks, Ryan. And we come to the second highlight talk, moving now more into the chemistry area. It's going to be given by Professor Emiliano Cortes at LMU Munich, who, as Anatoly said, started out actually as a Marie Curie fellow and then as a postdoc on R+ and was really instrumental at Imperial for the setup of the chemistry program there. And he's going to present the highlights both from the work at King's and Imperial that we managed to do over the last 6 years already. So Emiliano, if you share, and I mute, and all over to you.
Good. So thank you very much, Stefan. Thanks, Anatoly and Ryan, for the introduction. So I will present briefly some of the highlights on these 6 years in reactive plasmonics on the side of plasmonic chemistry and photocatalysis. So let's start from the very beginning and the idea of using these plasmonic materials for catalysis or for doing chemistry. And for that, I think it's first interesting or important to check the properties of these plasmonic nanoantennas when they are being illuminated towards chemical reactions, right? So if we think on these plasmonic interfaces or some kind of plasmonic antenna, so here we have a bow tie antenna that it's being illuminated, many phenomena happen at the same time on these antennas when we are illuminating with continuous wave lasers. So on the first hand, we have electric field confinement in these antennas, in these kind of like hotspots, which is like a very well-known effect of plasmonic antennas for a very long time. But as Anatoly mentioned at the very beginning today, for a long time, there was a lot of complaint in the community that plasmonic was a really lossy material and that we were not using that kind of like property, right? So the plasmon relaxation and the energy that it's been dissipated to the environment after the plasmon has been excited and how we can use that. And indeed, for chemistry, that's really important, right? So because besides the electric field confinement that happens in plasmonic nanoantennas or in the hotspots of plasmonic nanoantennas, these materials also absorb part of the light, and that absorption creates energetic carriers inside the material, right? These hot carriers, hot electrons and hot holes. And also at the end, these highly energetic electrons dissipates the energy through the phonons of the material, right? So we have mechanical displacements in the material and we have electron-phonon coupling into the material. And finally, we end up heating the structure by temperature, right? By increasing the temperature. So all these things happen at the same time. And also these are metallic materials, and as any metal material or as any heterogeneous catalyst, it has an inherent response due to the uncoordinated atoms on the surface, right? So this would be like the catalytic properties of the material in the dark without any kind of illumination. So at the end, if we want to understand how these plasmonic structures react or the reactivity of these plasmonic structures towards catalysis or some chemical reaction, we need to consider all these type of phenomena that happens at the same time. But also, if we think on an ideal reactor chamber for a catalytic reaction, many of these properties are really well desired as well. So indeed, the idea of thinking these plasmonic structures as reactors for chemical reactions, it's not far from what we do macroscopically nowadays for driving catalytic reactions, right? So the idea is, can we use these materials in order to absorb light, ideally sunlight, in order to drive chemical reactions in a cleaner way and in an energy safe way. And besides this, there is also something else behind, and it's the idea of how we compare this type of reactions with like thermal activated reactions. So nowadays in industry, most of the reactions that involves a catalyst, right? So heterogeneous catalytic reactions are driven at really high temperature, at really high pressure, right? So that's the way in order to trigger reactions. So we have a material that kind of like sits an activation barrier for the reaction, and then we need to increase the temperature or the pressure in order to achieve the conditions in which we can overcome the activation barrier of the reaction and generate products. So the idea of using plasmonic catalysts, so to excite the electrons in the material by using light, also opened the door in order to explore new reaction pathways on chemical reactions. So by the transfer of these hot carriers, for example, it has been shown, and it's still a huge debate, but there are some really nice and clear examples that you can reduce the activation barriers of some reactions by exciting plasmon modes and using exactly the same catalysts as before, but in a much milder conditions of reaction, right? So this idea of exciting plasmons and reducing the energy barrier of some reactions and having milder reaction conditions by using sunlight, for example, has attracted, well, the interest of many research groups. So I will show you a bit of what we have been doing in reactive plasmonics in the last years. And in order to understand that, I divided the talk in like 3 main sections, right? The first section, it's understand the physics behind these processes, right? What we just were discussing. And for that, there is something that we need. And in order to understand the processes like really at the nanoscale, we need to develop some single particle techniques. And this is still a really challenging field in heterogeneous catalysis, right? So even besides plasmonic catalysis, in heterogeneous catalysis, it's really challenging because if you think on the amount of molecules that you are generating on converting at a single nanostructure, it's really few, right? So there are nearly any technique, any analytical chemistry technique that can detect such a small amount of molecules. So we need to be creative in a way that we can track reaction conditions at the single particle level, because these may allow us to understand which of these phenomena plays a role in this plasmonic nanostructure. It's the temperature, it's the hot electrons, which are the reactive sites, how the structures react to the wavelength, and which is the power dependence. So all these things are much easy to understand and to explain if we go to the single particle level. And also this will allow us to create some ideas on the design of catalysts for the future, right? So what do we need to maximize? How we maximize the given property in the catalysts for given chemical reactions. So we did quite a lot of work in single particle plasmonic catalysis in order to try to understand this phenomena. And we developed some techniques, either based on electron microscopy or on super resolution microscopy, in order to track the chemical reactivity of these nanostructures. So the first idea that we had when we started working on this was to localize the reactive spots on the surface of these plasmonic nanoantennas, so where the reaction is taking place. And for that, we started with these silver bow tie antennas, these triangles here, and we used these really small gold nanoparticles in order to track where the reaction was taking place on the surface of these nanoantennas. So we used a trick here that we chemically functionalize these gold nanoparticles with something that reacts with the molecules that has been converted on the surface of these nanoantennas after we illuminated with the plasmon resonance wavelength. So here we can see that these two particles binded mostly in the hotspot, meaning that the reactions in this kind of like plasmonic structures started at the hotspot indeed. So after that, we moved into something a bit more elegant, and we tried to image the chemical reactions by using super resolution microscopy, so below diffraction limit of light. And in here, we have these trimer structures, so 3 rods. And when we illuminate with the polarization that matches one of the rods, we could displace the molecules on the surface, and we could replace that with another given molecule. So again, this image that we are seeing, it's below the diffraction limit. So we are looking inside the diffraction limit spot of the light, and we could functionalize, or we can work, we can release molecules within the spot by using the trick of exciting carriers in these plasmonic nanostructures. So this could allow, or this could open a door in order to functionalize selectively at the nanoscale with molecules given surfaces. And finally, once we kind of like understood how these things work, we could even show that by illuminating with 2 different wavelengths on the same structure, we can localize the chemical reaction on different parts of the structure. And this is really interesting because it means that by changing the wavelength, we can selectively choose the space in where the reaction is taking place. So we can be spatially selective on chemical reactivity, which is a really nice field, and it has been not so much explored so far. So this was our kind of like first approach in where we try to see the reaction and where the reaction was taking place and try to understand where the reaction was taking place and which was the main driving force behind the reaction. So, but besides that, so we developed a method in order to map hot electrons, which was based mainly on the idea of DNA paint, which is a super resolution technique that I will not go into too much details, but basically we bind molecules transiently on the surface of these nanostructures, and these molecules that are bind on the surface has a fluorophore, and we can track the fluorophore position, and for that we can reconstruct a super result image, right? So we generate a reaction that is based on hot carriers that can displace molecules from the surface, and that is what we image in this kind of structure. So where the molecules has been released, and this is where the electron has been excited. But we also look at temperature measurements, for example, at the single particle level, which we saw it was another of the components that can help or can trigger a reaction at the nanoscale. So if we want to understand which of these phenomena plays a role in a given reaction, we need to have techniques that can reach the single particle level and that can be computed together in order to see which of these mechanisms is the dominant one. So furthermore, besides hot electrons and besides temperature, we have also developed methods at the single particle level in order to track the energy of the hot carriers. So here we combined dark field spectroscopy and microscopy with one electrochemical cell, and we were able to track the energy of these hot carriers in a given reaction at the single particle level. So here we have gold nanoparticles, which are 16 nanometers in diameter, and we applied voltage, well, different type of voltage, until the reaction happens on the surface of the particles. And then we perform the same experiment in the electrochemical cell, but illuminating one of the nanoparticles and having the other one as a control. And what we could see is that the reaction, so when the reaction takes place, the nanoparticle changed from this green color to this orange color. And what we could see is that for the illuminated nanoparticle, that happens at lower voltage, right? So there is an electrocatalytic, photoelectrocatalytic effect. So the reaction is happening at a lower voltage. And this is due to the energy that the hot electrons are able to supply to the reaction in order to perform the reaction at a lower voltage. So by having that in mind, so by having like the idea of which are the energy of the carriers, which are the reactive sites, how much the temperature contributes to some reactions, how much the hot electrons contribute to some other reactions, we start also thinking on designing new plasmonic catalysts. And for that, the easiest way or the common way to do that is through working on the colloidal synthesis of nanoparticles. But in this case, we try to focus on synthesis, the synthesis of colloidal nanoparticles, mainly thought for plasmonic catalysis, right, to act as catalysts. And for that, there is a huge parameter space that we can explore, from the shape of the nanoparticles, the size of the nanoparticles, the material compositions of the nanoparticles. So all these things are things that we can play with in order to create better structures for plasmonic catalysis. So regarding that, I will highlight a couple of the works. So we have left out many things here because this is like a reduced doc. So we just pick some of the highlights. So in here, for example, we tested the idea of having bimetallic plasmonic catalysis systems, right? And this is kind of like important. So all the things that we have mentioned so far, it's how the reaction evolves when we excite the plasmon in the plasmonic material. However, plasmonic materials are not ideal catalysts for most of the reactions or the most important reactions, because they do not tend to have good properties for the absorption of molecules, the dissorption of molecules, and to lower the activation barriers of the reaction, right? So that's a good catalyst. But plasmonic materials are not good catalysts for many reactions. So rapidly in this field, it started the idea of combining materials. So what happens if we have a plasmonic material that can harvest the light and that can excite the plasmon modes, but we have also another material which is good in catalyzing a given reaction. And in here, for example, Jorge from King's explored the idea of having this silica support big nanoparticles, And on top of that, we have small gold nanoparticles that are decorated with platinum clusters. So here we're combining the ability of gold in order to harvest light and excite plasmon, and the ability of platinum in order to catalyze chemical reactions quite efficiently. So Jorge tested like many different things from the amount of platinum that you can load, the size of the plasmonic nanoparticles, and they tested this towards the degradation of some organic dyes. And in here you can clearly see, for example, from the field enhancement picture, what happens with these silica spheres with the gold nanoparticles, and what happens once you add these platinum clusters, right? So you could see here that the enhancement in the near field, it's huge when you add these really small platinum clusters, and they also behave much better towards the degradation of organic dyes when the platinum is present. And they explore here like all the different parameters that can affect the construction of this type of plasmonic catalyst. We also moved and we also started thinking on new ideas or new catalysts specifically designed for plasmonic catalysis, right? So there are plenty of different colloids in the literature and for many different types of applications, but so far for plasmonic catalysis, I would say it's a quite new field, and there are very few colloids that has been really thought for these type of applications. So towards that, we also designed new catalysts, which has maybe like a bit more weird shape, but also with the idea of, for example, what we need is to have like a really high near field enhancement and absorption inside the nanoparticle in order to have higher temperatures and hot electron production. So in here, we designed these particles, which we call particle in a frame, because we design these structures where you have like a central particle, which is surrounded by a frame, in this case, made out of gold, and the enhancement in this inner particle, it's huge. And also the available area for molecules to sit on top of these nanoparticles, it's huge, right? Which is something that we also need in catalysis. We need like a lot of surface area because the reactions happens on the surface of these nanoparticles. So another type of nanoparticles that we also designed specifically thinking on plasmonic catalysis with this kind of trimer structures in where we have like 3 hotspots in this single structure. And we coated these gold nanostructured trimers with a thin shell of platinum and palladium, which are also really good catalytic materials. And we prove in here, which is the effect of having hotspots in the structures, right? As we know, and as I showed in the previous example for the single particle measurements, hotspots are a key principle in order to build efficient plasmonic catalysts, because the field can be highly enhanced inside and outside the nanoparticle, right? So the absorption and the confinement of light is huge when you have hotspots present. So finally, the last thing regarding colloids that we designed and we fabricate for plasmonic catalysis, oops, sorry, come back. So the last thing is that we start thinking on patterning surfaces by using these colloids. And the idea of patterning surfaces is that when you have these plasmonic colloids, and you want to perform chemical reactions by using the colloids in solution, there is a problem of the penetration depth of the light inside the solution of colloids. If you have a really concentrated solution of colloids, what might happen is that most of the light gets absorbed by the first layers of colloids, but then in the bulk, inside the solution, the catalysts will not have any kind of illumination, right? Because most of the light have been already absorbed or scattered by the first layers of colloids. So then an idea is to place those colloids that has been designed for plasmonic catalysis in 2D, right? So to create surfaces where we can pattern these colloids in order to have like a maximum light excitation of the nanoparticles and also exposed surface of these catalysts. And for that, we have designed different methods in order to pattern these kind of colloids on different type of substrates, right? So conductive substrates to perform photoelectrochemistry or different conductive substrates or dielectrics. So the last thing I would like to mention, so we went first for the single particle techniques that allow us to understand a bit of the physics behind. Then we move into the synthesis of colloids specifically targeted for plasmonic catalysis. And finally, I will just show you some examples on electrified interfaces, which is the other topic that we have been also working quite a lot. And the idea here is that we have an electrical contact and we can do electrocatalysis, but also excite in the plasmon mode, so photoelectrocatalysis. Or we can do different type of applications by having electrified interfaces. And here, one of the main examples, it's this. example developed by King's College on reactive tunnel junctions. So here we have an anodized alumina that has been coated with gold, electrodeposit gold, and we create these kind of like tunnel junctions in where there is an electron hoping in between the gate and the nanorods, and these electrons can have, well, two routes. So one, it's that they are being transferred through the tunnel junction as a hot carriers into the gold structures, or the other one, it's that the electrons can be transferred radiatively and excite the plasmon modes in these gold nanostructures. So if we have enough voltage applied into the gain, what happened is that we have two ways of exciting carriers in the gold nanostructure, either by tunnel junction of the carriers or by exciting via radiatively decay of the electrons. So here they have shown that if we have this tunnel junction here, so you can see here in between the gain and the gold rods, there is a tunnel here, which is this phenomena that I just explained. But if you fill that tunnel junction with different molecules, then you can have a reactive tunnel junction. So the molecules can react due to the presence of these hot carriers that are being tunneled from one side to the other, and also due to the hot carriers generated by the plasmon decay. So this also emits a lot of light because the carriers can also be can decay radiatively, emitting light. And here you can see a macroscopic picture, right, of the device emitting light. So we have these kind of reactive junctions that can both react with molecules or emit light depending on the decay channel that is favored. So towards the end, one of the most prominent applications would also be to have copper nanorods metamaterials. So copper is one of the, probably it's the only really nice plasmonic material in the visible regime, but also from the catalytic point of view. So copper, it's a really well-known catalyst for CO2 reduction and the generation of C2 products, right? So CC coupling reactions. So copper, it's a really interesting material for us because it has both the plasmonic properties and some really nice catalytic properties towards CO2 reduction. And this is the work from Anastasia, from King's as well, where she has been working on the CO2 reduction, electrochemical reduction, and plasmon excitation on these copper metamaterial nanorod surfaces. So this is similar to the previous example where we have like a template, and then we have, well, in this case, copper and copper oxide on the surface. And this material can also support plasmonic resonances, and you can excite the material, and you can also perform electrochemical measurements, right? So you can do photoelectrocatalysis on this metamaterial, exciting the plasmons and electrically contacted in this cell. And the very last example before I finished, it's something that we also started working recently, and it's the idea of using hot electrons, or how we can sense the hot electrons in these plasmonic materials. And for that, we have been working on the idea of having quantum dots in an electrochemical cell. And what we have seen is that quantum dots can be charged with electrons when you change the voltage. So when you apply a voltage in this electrochemical cell, and the optical properties, the emission, for example, the PL lifetime or the blinking of these quantum dots can be strongly changed or modified by the amount of carriers that are being introduced into these quantum dots. So we have done that with an electrochemical cell, but our idea is that hot carriers from plasmonic structures can also maybe be transferred to these quantum dots, and we can use the quantum dots as a way to sense the presence of the hot electrons and the transfer of hot electrons in plasmonic structures. So, sorry for the rush. And as I said, I left many things out here because we have to select some of the things for the talk today. And this has been mostly the work from people from King's and Imperial during these years on plasmonic chemistry and photocatalysis in many different fields. And I will not mention each of them, that I will just mention everybody, and also EPSRC for the funding. And yes, I'm open for questions.
Great, thanks a lot, Emiliano. We actually have two questions already in the chat. So Zayats is asking you, what is more efficient for catalysis, an island structure or a core shell structure? These islands can affect the kinetics of the catalyzed ions. Any general view on morphology and efficiency?
Okay, so what we have learned in general is that something kind of like expect at some point, and it's that spiky structures or structures which has a lot of tips, they are much better in terms of hot electron generation or emission or reactivity, right? Because the electrons are being generated really close to the surface, and that means that they reach the surface really fast and with a lot of energy. While if you have a less spiky material, or let's say more like rounded material like spheres or rods, then you have the problem that the electrons lose a lot of energy before they reach the surface, and many of the carriers are lost inside the material. So anything that has spiky tips would make it better in terms of quark electrons fraction for molecules.
Okay, and then we have a second question from Pritu. Interesting one, very interesting one actually. So what is your view on using deep UV 200 to 250 nanometers radiation and then the plasmonic materials, aluminum and rhodium, instead of visible spectrum and gold silver for catalysis?
Well, it's interesting. The main problem there is that what I feel is that the new door that this kind of like field, it's the possibility of using sunlight for these processes, right? So titanium dioxide or zinc oxide, for example, are semiconductors that has been widely used in photocatalysis, but the main problem that they have is that they absorb quite far from the sun emission. So I think that one of the highlights of plasmonics is that you can tune the absorption all over the visible spectrum, and that would favor or would like allow in principle in the future to use sunlight for performing these processes. But we have also been working a little bit on UV light irradiation on some semiconductors, and there is a poster in the poster session from Daniel Glass from Imperial, which he shows the possibility of creating defects in semiconductors by using UV or UVC light, and how that impact on the reactivity of these materials.
Okay, great. Any other question from anyone at this point? If not, let me please just remind everybody again, please stay around for the roundtable discussion this afternoon, and maybe some more questions will materialize by then. Okay, so thank you, Amy. And now we move to our last highlight talk, moving from chemistry and catalysis to applications of plasmon-induced charge carriers and transfer in optoelectronics. And that talk is going to be given by Anton from King's College. So Anton, if you can share your screen.
Perfect. Thanks, Stefan, for the introduction. I'm giving the highlight talk about the reactive plasmonic highlights on the optoelectronics, fundamental hot carrier dynamics, and nonlinear optics. So the reactive plasmonic project is focused on the studying and applying and using the strong interaction between optical fields and hot carrier ensembles created by the decay of surface plasma polaritons in materials in various ways. And within this scope, we explored various possibilities, including creation of the optoelectronic devices, allowing us to either convert the optical signals into electronic signals or vice versa, the fundamental hot carrier dynamics, some of which was already mentioned by Ryan before, which are important whenever we want to use some alternative novel plasmonic material as titanium nitride or copper sulfide, which I will be talking here in a bit more detail, and as well as nonlinear optics, which use a medium under the plasma excitation as a means to control light with light. So going to the first part of the talk, the optoelectronics, or in particular the IR hot carrier photodetection. So the conventional photodetectors utilize the carrier separation followed by interband absorption in semiconductor, which is fundamentally limited to bandgaps of materials and therefore cannot be easily extended to new wavelength ranges, in particular for long wavelengths. Therefore, a search for different photodetection approaches is ongoing, and one of the such approaches which has recently gained a lot of attention is the possibility of using hot carriers to demonstrate the subband photodetection. Usually, the hot carriers generated in a plasmonic metal are being harvested then in an adjacent semiconductor after tunneling through the Schottky barriers. And you can see here that this idea has already been explored in various means, in various sample and experimental geometries by many different groups around the world. And within the reactive plasmonic projects, we also investigated different structures, different materials, different geometry for that. For example, the titanium nitride silicon compound, which uses the native oxide layer for efficient harvesting of photoelectrons, the strontium titanate detector, and for example, photothermal Voltaic graphene detector. You can already see from this table here that these detectors, even as a proof of principle demonstration, apart from offering additional non-explored geometries and material compositions, already allow us the sensitivity values approach to the state of the art, and they can be further improved. Unfortunately, due to the time constraints, I won't be able to talk about the titanium nitride and strontium titanide detector. I will focus on the photothermal Voltaic graphene detector. So the detector looks approximately like this. So it consists of the layer of gated graphene layer with two top gold electrodes, which are intentionally made asymmetric. One of them is just a gold bar, but the other contact hosts a series of plasmonic antennas, which offers us the local field enhancement, as well as the expected to generate the hot carrier population, which will be driving our photothermal voltaic effect. In fact, photothermal voltaic effect in graphene metal junction has already been studied before in different detectors, but usually it's just being driven by difference in Z-big coefficients between graphene with a metal overlay and surrounding graphene. So it's only observed as a contact areas. So that's exactly what we see when our non-plasmonic contact is illuminated with light. What we observe the photovoltaic response, which doesn't have obviously the plasmonic enhancement, and at the same time show the non-monotonous dependence as a function of gate voltage, which vanishes at a condition which corresponds to the flat band condition in graphene, which is expected for this kind of effect. However, everything changes if we illuminate our plasmonic contact. In this case, we first of all observe the plasmonic enhancement of the effect, and secondly, the whole curve on the bottom here got shifted upwards and no longer crosses zero, showing that there is an additional contribution which we don't take into account normally. So this additional contribution was identified as being produced by the hot electron diffusion within the graphene channel. The hot electron produced by the plasma excitation, the diffusion inside the graphene channel, and therefore produce a photothermal voltaic effect depending on the gradient of the electronic temperature. So finally, we measured the speed of this detector, how fast it can react, by using some modification of the pump probe setup. And it shows that most of the detectors mostly recovers within the picosecond time scale, which means it can be used up to a terahertz frequency range, which is not very common for photodetectors and is definitely advantages in the field. So another optoelectronic part, which I'm going to show, is opposite, is actually focused on converting electrical signals into light. That's our contribution to the design of a sub-wavelength coherent surface plasma laser. For this, we chose the ring geometry, the ring cavity, based on the standard 3-5 semiconductor technology, coupled with a gold film on top. This structure utilizes a very efficient electron injections through the shallow Schottky barrier at the interface, and is expected to show us a threshold at about 30 kiloamps per square centimeters at room temperature with a single mode operation, and we expect it to have at least 2 orders of magnitude higher efficiency than a conventionally electrically pumped plasma lasers. In addition to developing devices, it's very important to understand the fundamentals of hot carrier dynamics. And this brings me to my second part of the talk, the hot carrier dynamics in the novel plasmonic materials. Some of these results you have already seen in Ryan's talk about titanium nitride. Here I'm going to focus on a different plasmonic structure, plasmonic materials that was also studied within the project, which is copper sulfide. So in the wild, copper sulfide is the generally doped semiconductors, which you can find as this blue naturally occurring mineral. In the lab, however, you can manufacture it in the form of nanoparticles like here, which produce a strong, very good quality local surface plasma resonance in the infrared close to telecom wavelengths, which in addition to being cheap, abundant, and chemically stable, make it very desirable alternative material. A lot of effort nowadays is being devoted to manufacturing and functionalization and characterization of such materials. However, very little effort is actually devoted to the fundamentals of hot carrier dynamics, and we try to fill this gap by using the standard pump probe technique, starting from the initial femtosecond timescale with the picosecond timescale. In the picosecond timescale, we observe all the standard stages of photoelectron decay, like with the emission of phonons. However, our main advantage here is that we were able to tap into the initial non-equilibrium stage of the decay, which was shown to be very fast, less than 20 femtosecond, comparable to graphene, and even shorter in the nanoparticles compared to bulk crystals, all in agreement with the theory, which is very advantageous from the point of application for ultrafast switching, for example. An unexpected result of this research was that we also were able to observe for the first time the excitation of the coherent lattice dynamics, which are two different optical phonon modes excited coherently in the material, and also can be advantages both from fundamental study of electron-phonon interaction as well as coherent control, for example. So the last part of my talk, which will be devoted to nonlinear optics. So nonlinear optics has found its way nowadays in various pieces of technology, ranging from frequency conversion, optical modulation and switching, pulse shaping, even quantum communications. For example, when optical modulation is concerned, the standard state-of-the-art commercial technology is using the Pockels cell, which is a nonlinear optical device, which offers you gigahertz modulation, having a centimeter-sized nonlinear crystal. As you can see, and the search for alternative nonlinear materials is continuing. And as you can see from the graph here, which lists the third order nonlinear susceptibility, which is relevant for optical modulation and switching, most of the standard materials follow the same trend along this graph. And some non-parametric metamaterial and constant linearities here can actually go away from the common trend, allowing to explore a different regions in the parameter space. So it gives additional incentive into studying this effect in these materials. So I must say that in this part of the talk, I joined together two different kinds of nonlinearities, not only conventional parametric nonlinearities, but also non-conventional, not so widely used non-parametric nonlinearities, which involves first storing energy in a photoelectron ensemble and then using this energy to affect the light. So as an example of such non-parametric nonlinearities could be our results on ultrafast polarization switching in plasmonic nanorods. So for this, we build up upon our long expertise in making this scalable, very convenient plasmonic nanorods composites, which are designed to be uniaxial material, in addition to being plasmonic. And because it's uniaxial, excitation of the hot carrier ensembles in the material affect both ordinary and extraordinary refractive index. For example, in this particular case, mostly extraordinary, which allows us to demonstrate the rotation of the probe beam if it's capable of being affected by both extraordinary and ordinary refractive indexes. We indeed are able to observe the strong rotation of the probe beam, as well as change in ellipticity governed by the control beam, as well as the rotation without the control beam if the probe beam is made powerful enough, the so-called self-rotation. We further built upon this idea by making the structure optically stick, in which case we can produce a hot carrier population which is non-uniform inside the structure and also evolves by itself through the photoelectron diffusion and photoelectron decay in the material, and while during the evolution interacts differently with optical modes in the structure. This gives us additional degree of freedom to control, for example, by tuning either pump wavelengths or probe wavelengths in a fixed structure, we can change how the hot electron population overlaps with optical modes and control the mentioned above polarization switching by using that. So as shown here in the bottom of the slide, with either tuning the pump or probe wavelengths. A similar idea, but entirely different realization, was used to demonstrate a plasma-induced optical anisotropy in a graphene layer. For this, we made a rectangular lattice of cylindrical plasmonic dots on top of graphene. This structure is in plane isotropic, or more precisely has a fourth order rotational axis, which is too high to be observed in linear optical response or even in nonlinear second order optical response. Therefore, anisotropy is not expected under the normal incident. However, everything changed when the plasmon resonance is excited in the plasmonic dots here. In fact, the strong coupling between the plasmonic near field and graphene through interband absorption gives rise to the hot carrier population in graphene, which has symmetry lower than the symmetry of the lattice itself. In fact, the symmetry mimics the symmetry of plasmonic dipolar mode rather than the symmetry of the structure. We have been shown that in agreement with the theory, this long-lived anisotropy, which is created as a result of this, is not dependent on the structure itself or its relative orientation to the light, and only dependent on the relative angle between the polarizations of pump and probe. Moving to a more conventional parametric nonlinear optical processes, a lot of effort in the project was devoted to studies of the so-called epsilon near zero materials, in particular the indium tin oxide. In these materials, you can observe a crossing of the real part of the electric constant with zero, and you expect to have an enhancement of all nonlinear processes around this point due to the strong local field enhancement in the interface. For example, in the case of sulfaction of light, this can be directly seen from the expression of the nonlinear induced refractive index. It can be further enhanced if you couple the epsilon near zero material with the plasmonic structure. And this what was implemented within the RPLAS project. For example, we created the combined structure which couples the sub-wavelength indium tin oxide layer with a rectangular array of plasmonic antennas designed so that we achieve an overlap between the epsilon near zero resonance and the antenna resonance, which allowed us to achieve a strong coupling with more than 100 millielectron volts bandgap here. And in this condition, we assess the structure by using the Fourier mixing process in a degenerate Fourier mixing process in a geometry when it mimics negative refraction. The geometry is shown here on the slide. And we've seen that in the strong coupling condition between the epsilon near zero and plasmonic resonance, we observe the 14,000-fold enhancement of negative refraction as compared to the Bayer ITO. Similar idea was used to demonstrate the enhancement of second harmonic generation on an ITO film coupled with the array of triangular plasmonic antennas. For the triangular system, the symmetry dictates that the second harmonic generation will be symmetry allowed even at normal incidence. And more than that, the circular polarized fundamental will only create a circular polarized second harmonic with opposite helicity. And that's exactly what we observed in the experiment. Like left circular polarized fundamental gives rise to right circular polarized second harmonic and vice versa, enhanced in the vicinity of the epsilon near zero condition. And we as well observe, like in the previous slide, we observe 4 orders of magnitude enhancement of the second harmonic as opposed to the Bayer indium tin oxide. However, I have to say that since the second harmonic generation at normal incidence for Bayer indium tin oxide is forbidden by symmetry, then this enhancement factor is only limited by experimental errors and could in principle be much, much bigger. When we incline a sample a bit, so therefore allowing the symmetry non-forbidden components for the second harmonic, even for Bayer ITO, I have to, it's important to know that even in this case, the nanostructure enhanced nonlinearity is many orders of magnitude stronger than the Bayer ITO. So in conclusion, we've explored various ways, various mechanisms of the light-matter interaction between the plasmonic structures and light and hot electron ensembles in plasmonic materials, and utilized it to create various devices, optoelectronics and nonlinear optical devices, as well as the fundamentals of hot carrier dynamics in novel plasmonic materials. Thank you for your attention. I will be happy to answer questions.
Thanks a lot, Anton, for the overview talk. Very nice. So I don't see any questions in the chat at this point. Does anybody want to ask something now verbally? Nobody right now, also nobody in the chat. Well, again, this afternoon there are more opportunities. So I think then let us conclude the talks. And what we are going to do now to finish up the morning session is we are coming to the Flash poster presentations, which will be a video that Megan, who has made this whole event here possible, as also over all of the last years, has assembled. And we will play this now. And if you have a question for a particular poster, again, you are welcome to put the question in the chat.
Hi, my name is Daniel Glass, and I'm going to briefly tell you about my poster, which is on the effects of photo-induced surface vacancies on photocatalytic metal oxide semiconductors. Oxygen vacancies are some of the most reactive sites on metal oxide semiconductor surfaces. They can drastically affect the physical, chemical, and electronic properties of your film. For example, they can change the color, they can change the reactivity, and they can also change the band structure by inducing defect states. As a result of this, inducing oxygen vacancies on your surface or on your material can drastically affect the charge transportation and the absorption of molecules, the interaction of molecules with your surface. The reason why you'd want to do this is because you can get strong positive effects of oxygen vacancies even in very low concentrations. A few parts per million of oxygen vacancies can have a massive effect on your physical and chemical properties of your film. And therefore, you can use oxygen vacancies to tailor to design properties of your film to be more reactive or to be more electronically, have a better charge transportation. However, the nature of vacancies themselves is very elusive. They're very difficult to detect, and they're very hard to understand to know how the concentration of defects that have been induced and how the concentration affects the overall performance of the film. In addition, these vacancies can form in situ during photocatalytic or different chemical processes, and therefore they can affect the way your reactions are happening whilst they're occurring. On top of that, vacancies are not generally probed under reactive conditions. They're very difficult to probe, and therefore often done through scanning techniques under ultra-high vacuum, very low temperatures, or with single crystals. So in the conditions of the samples that are very far from ideal reactive conditions. And therefore, there's a central need in order to probe vacancies under reactive conditions to clarify their effect on the material system and how they affect different mechanisms. In this work, we probe for photo-induced oxygen vacancies on the surface of metal oxide semiconductors through a technique called PIRS, photo-induced enhanced Raman spectroscopy. Pre-irradiating with UV light causes oxygen vacancies to form on the surface of these metal oxide semiconductors. The oxygen vacancies then interact with analyte molecules, enhancing the Raman signal beyond the surface enhanced Raman signal that was there before, or the SIR signal. You can track the formation of vacancies by tracking the steady increase of the Raman signal over time. However, after the UV has been switched off, and upon exposure to either air or water, the oxygen vacancies heal up, and therefore a steady decrease in the Raman signal can be seen, eventually returning back to the original SIR signal. Therefore, we can use the changes in Raman to track the formation and healing of oxygen vacancies over time. In this work, we use PIRS as a tool to probe photocatalytic particles under reaction conditions to track the formation and healing of oxygen vacancies. We found that the concentration of vacancies does not directly correlate with the photocatalytic enhancement of the film, the photocatalytic activity of the film. However, a Goldilocks concentration can be found for ideal photocatalytic efficiency. In addition, longer-lived vacancies appeared to correlate with higher photocatalytic activity. For more information, please have a look at my poster or be in touch. Thank you very much.
Hello, my name is Anastasia, and today I would like to present a poster about copper-based metamaterials for photoelectroreduction of carbon dioxide. So first, we developed a method for the fabrication of large area copper nanorod metamaterials with design dimensions using several techniques, such as sputtering, aluminum anodization, electrochemical deposition, and chemical etching. Our fabrication method is highly controllable and can be easily applied to a large surface areas with an added benefit of a high uniformity. Copper as a material has a lot of advantages, such as high natural abundance and low cost, that makes this material very attractive for commercial exploitation. But also, copper nanorod metamaterial have a strong tunable plasmonic response. In principle, by changing, for example, the radius of rods, the plasmonic resonance can be tuned to catalyze chemical reactions that occur on the high reactive surface of copper nanomaterials. Copper nanomaterials are often at a disadvantage when compared to noble metals because of their potential for oxidation. Reframing this problem and instead harnessing the photocatalytic properties of copper oxide, we created core shell copper oxide metamaterial by controllably growing copper oxide layers with a nanometric thickness using the technique of anodization. This process can be monitored optically in real time using unsewed visible light spectroscopy. An examination of this result clearly reveals a dramatic redshift of the L resonance in experiment but also in simulation due to the growth of the oxide layer. In addition, we also optically observed the reversibility of these processes. Furthermore, copper nanorods with a surface oxide layer can be used as catalysts for photoelectrochemical reduction of carbon dioxide. The electrochemical measurements were performed using an electrochemical H cell, where copper nanorod sample is our cathode, where carbon dioxide reduction occurs. We also studied the photoelectrochemical behavior of copper nanorod catalyst. Under illumination with red laser, the current was enhanced in the magnitude when using negative potential. That means that the incident light can actually promote reduction reaction when plasmonic catalyst is used. As expected, for a hot carrier-driven process, the plasmonic photocathode copper nanorods exhibit a linear photocurrent response with respect to incident light power. Next step is now to quantify and qualify resulted products via NMR and study catalyst selectivity. To summarize, this presents a great opportunity for driving photoelectrochemical reactions, such as carbon dioxide reduction reaction at the nanoscale, using hot carriers from plasmonic metal nanostructures. Furthermore, we can combine the well-known catalytic behavior of copper oxide with plasmonic enhancement of metallic nanostructure to produce a highly efficient photocatalyst for carbon dioxide photoelectrochemical reduction. Thank you very much for your attention.
Nanocatalysts based on plasmonic effects are of interest for many reasons within the field of chemistry and solar energy, such as hydrogen generation, water purification from organic pollutants, bacterial disinfection, and many other applications. While conventional catalysts rely on effects derived on surface adsorption, plasmonic photocatalysts depend on energetic charge carriers generated by plasmon decay, which are then transferred to an external reacting agent, triggering a chemical transformation as depicted in the central picture. Here, we studied heterostructures consisting of silica cores decorated with gold nanoparticles, which are coated with platinum. Gold is a plasmonic material that provides the hot carriers, and platinum is a co-catalyst that facilitates surface adsorption. The catalytic efficiency was studied as a function of quantity of gold and platinum by varying the size of gold particles and the loading of platinum on the surface of gold. As a benchmark, the degradation of methylene blue was studied. It was found that the reaction is very sensitive to platinum on the structure, increasing as the platinum loading increases up to a certain point. The optimal design consists of gold particles fully coated with a platinum layer, along with platinum nanoclusters at the surface. At these nanoclusters, field enhancement is substantial, and they become hotspots for efficient hot electron generation and extraction. At these spots, it is more likely that a hot electron would be extracted. These nanoclusters are crucial for the enhanced performance. The optimal design consists of 12 nanometer gold nanoparticles and 3 nanometer platinum nanoclusters. Other catalysts usually consist of complex combination of different materials, such as metals and semiconductors, and some are challenging to synthesize. In our approach, the synthesis process is less complex. Our nanocatalyst was compared to other catalysts recently reported in the literature, and outperformed some of the most recent and popular photocatalysts used for methyl blue degradation. Not only methylene blue, but all organic pollutants sensitive to superoxide anion species can also be degraded by the designed photocatalyst. The proposed plasmonic heterostructures are not limited to water purification from organic dyes. By engineering an appropriate plasmonic nanostructure in conjunction with the choice of a catalytic metal suitable for a given reaction, it is possible to maximize a reaction rate due to hot electron excitation and transfer. The developed approach allows for optimization and exploitation of plasmonically generated hot carriers in a wide range of photocatalytic applications. More information can be found in the references at the bottom of the poster.
Hi, in this poster, I'm going to talk about how to control the enhanced Raman scattering by using plasmonic waveguide. As we know, Raman scattering can be used to identify the chemical structure of molecules. However, the efficiency of spontaneous Raman scattering is too weak. In order to overcome this problem, lots of techniques has been developed. For instance, the surface-enhanced Raman scattering. But all those previous techniques are limited either by the poor control of light scattering or limited by the narrow bandwidth of Q factor. So in order to overcome those problems, here we are going to use the unique features of plasmonic waveguide to achieve the Raman scattering with both good enhancement and well control. In this picture, shows the structure of the slot plasmonic waveguides, which we are going to use, which has two pairs of antennas. So first, we investigate and prove those waveguides can be used to well control the incident light. And then we shows those structures can also be used to control the Raman scattering of the molecules which were bonded to the waveguide. Importantly, we shows more than 10 to 4 times Raman enhancement can be achieved compared to the molecules which were bonded just to the surface of gold film. So in order to understand the mechanisms of the Raman enhancement of the waveguide, we developed a theoretical model within which both the light field and the Raman scattering field were taken into account. So our model can be used to lightly reproduce our experiment data by using only one parameter, which is the propagation distance of the surface plasma polariton. And finally, by measuring the Raman scattering, which were coupled to the free space and which were coupled to the waveguide. So we precisely determined that more than 99% of the Raman scattering photons will be coupled into the waveguide instead of going to free space. So which means here we can offer a unique way to achieve this unidirectional scattering of the Raman scattering. In conclude, so here we propose a unique and novel technique to precisely control the enhanced Raman scattering, which could be used for more precise chemical identification in the near future. Thank you.
Welcome to our poster entitled Copper Sulfide Nanocrystals as an Alternative Plasmonic Material. Copper sulfide is a mineral which, owing to its crystal structure, has very interesting properties that render it as an advantageous alternative to conventional plasmonic materials. These properties include a natural hyperbolicity in the optical visible spectrum, while at the same time also being anisotropic and plasmonic in the near infrared. Subsequently, these nanocrystals show a dominant localized surface plasmon resonance in the near infrared, which has been demonstrated to be widely tunable by changing the size and shape of the nanoparticles, and its range can be between 800 to 1600 nanometers. This range ideally places copper sulfide in a desirable position filling the gap between conventional metal and metal nitrides operating in the visible and conductive oxides beyond 1500 nanometers. In this poster, we further also demonstrate our study of large-scale thin uniform films of copper sulfide nanocrystals. We use two very different methods of fabrication, one being electrophoretic deposition and the other using chemical functionalization of the substrate to bond with the nanoparticles. Through both these methods, we were able to make smooth, thin films which we then use for various optical characterizations. Interestingly, the extracted optical permittivity of the effective medium of these thin films predictably had a plasmonic character to it, and we subsequently demonstrate the presence of surface plasmons on these nanocrystal films. We further show interesting physics of thermalization of hot carriers in copper sulfide bulk and nanocrystals using pump and probe transient measurements. The result shows that thermalization happens faster in copper sulfide compared to conventional metals owing to the lower carrier density in copper sulfide. We also detect coherent optical phonons in the bulk CUS crystals as well as in the nanocrystal films. Finally, we also demonstrate experimentally that the LSPR in copper sulfide nanocrystals can be tuned in a wide range and with a good reproducibility by doping these particles with zinc using an ion exchange synthesis procedure. The resulting particles show a consistent redshift in their LSPR peaks as the ion exchange synthesis temperature was increased, which we attribute to increased zinc doping. So if you want to learn more about these characteristics of copper sulfide, about the thin film fabrication, about the pump probe transient measurements and the interesting physics, and how to tune these particles to more redshifting resonance, please visit our poster. Thank you.
Hello, I'm Killian from King's, and I will be discussing our work in cavity-enhanced photodetection. As we know, hot carrier plasmonics offers many opportunities across a wide range of technologies. In particular, sub-bandgap photodetection afforded by plasmonic Schottky devices enables integrated detectors operating beyond the bandgap limit. Here, we demonstrate a cavity-based platform for both enhancing the sub-bandgap current and also providing a means for dynamic reconfiguration of the operating wavelength. The proposed geometry is shown in Figure A. An optical cavity is formed between two gold films, which permits the resonant generation of surface plasmon pleurodons, SPPs, via resonance scattering from a grating incorporated into one of the mirrors. These SPPs subsequently decay, producing hot carriers that give rise to a photocurrent. Thus, by actively controlling the resonant conditions, we can directly modify the wavelength of resonant plasmon generation, and hence, by extension, the peak photodetection wavelength. Initially, the photocurrent was mapped from an isolated grating, i.e. without a cavity, in order to confirm the plasmonic origin of response. The output from an uncoated cleave fiber was scanned across the grating, with the resulting current recorded for each position. A clear hotspot with dimensions close to the milled grating is evident in the current map with the cross-section shown in Figure B. Once SPP-induced photocurrent was demonstrated, the second mirror, formed from the cleave fiber coated in a 10 nanometer thin gold film, was put in place and scanned in the Z direction in order to elucidate the influence of optical cavity modes. The spectral response of the cavity-based photodetector is shown in Figure A. The cavity modes are clearly apparent, providing much greater photocurrent than in the case of off-resonance, due to resonance scattering from the grating. This scheme also enables direct control over the detection wavelength, as the resonance conditions can be dynamically tuned. This is highlighted in Figure A, as the peak response is mechanically tuned over the spectral range of the laser by altering the Z position of the top mirror. The photocurrent from this resonance system is roughly 5 times greater compared to the off-resonance condition. The underlying mechanism of this resonant enhancement is further clarified via simulations presented here. When the cavity is on resonance, a clear enhancement is observed in the intensity of substrate SPPs. This leads to metal absorption at the substrate interface that is about 10 times greater than in the non-resonant case. The enhancement is further clarified by Figure C, which shows the electric field along a line in the Z direction as the upper mirrors move through the resonance conditions. In summary, we have successfully performed a proof of principle experiment illustrating the cavity-enhanced and wavelength tunable photocurrent provided by a cavity-based architecture. The device exploits cavity-driven plasmonic modes to greatly improve the performance of sub-bandgap photodetectors. A 5-fold increase in the photocurrent was recorded compared to the non-Mesnik case, illustrating the potential of this approach, which can be adapted to include other plasmonic structures. We have also demonstrated dynamic reconfiguration with respect to the operating wavelength, thereby expanding the functionality and paving the way for future tunable photodetectors. Thanks for your attention. Cheers.
Hi, I'm Zayats from the group of Dr. Riccardo Sapienza at Imperial College London. The development and characterization of versatile nanostructured materials with enhanced nonlinear optical properties are relevant for integrated and energy-efficient photonics, and my research focuses on the nonlinear characterization of such nanomaterials. In this poster, I am presenting the efficient third harmonic generation from organic halide perovskite nanocrystals, more specifically from former medinium lead bromide nanocrystals dispersed in an optically transparent silica film. Easily integrable halide perovskite nanocrystals are exciting due to its stability, strong absorption above band gap, and a high dielectric constant which promotes strong nonlinear responses. The material synthesis and linear characterization presented here were carried out by Andrea Rubino in the group of Professor Hernan Miguez at the Institute of Materials Science of Seville. My work involved the determination of the third-order nonlinear susceptibility of the former medinium lead bromide nanocrystal sample, which quantifies the strength of the third-order nonlinear response. By excitation with a pulsed femtosecond laser, we observed the efficient third harmonic conversion in a wide spectral range in the near-infrared, with maximum conversion near the excitonic resonance of the nanocrystals, where the electron density of states is largest. We evaluated the maximum third-order nonlinear susceptibility of the nanocrystals by fitting an analytical model to the experimental third harmonic data. This model takes into account the optical properties of the sample, as well as the phase mismatch and absorption over the sample thickness. Finally, by considering the volume distribution of the nanocrystals in the silica matrix, the maximum third-order nonlinear susceptibility of the former medinium lead bromide nanocrystal was found to be 1.46 times 10 to the power of minus 19 meter squared over volt squared. This is the same order of magnitude as the inorganic lead halide perovskite nanocrystals. If you found this work interesting and would like to learn more, please visit my poster, and I welcome any comments and questions.
Hello, I'm Xiaofei. I would like to tell you about our work on gold nanoantennas for generating photon pairs for quantum imaging. This is a technique presented by researchers in the Dillinger group recently, and it is technically very interesting, because you can image an objective in the infrared while detecting only visible photons, where detectors are best. For this, you only need a good source of photon pairs with one photon in the visible and one in the infrared, and we want to build such a source. On the top right, you can see our design. We have 3 resonances, such that you can pump at 850 nanometer and get pairs at 550 nanometer and 1550 nanometer. Of course, in the future, we would like to push this further into the infrared, where many molecules have characteristic absorption bands. For our characterization, we make use of a technique called stimulated emission tomography, SET. The basic idea is to study a spontaneous process, such as SPDC, which delivers photon pairs indirectly via the corresponding stimulated process, DFG. In order to estimate the SPDC pair generation rate, you need to divide the DFG signal by the number of photons that were used for stimulating the process. So far, we could apply this technique to a sample that were used for nonlinear frequency mixing studies previously. The framework is established now, but the best we could get out of this old sample is an estimated SPDC pair generation rate of 0.4 Hz. So we want to use our new antenna to increase this efficiency. We have not measured DFG yet with it, and not directly compare the samples, but we could show that the new sample does indeed support frequency mixing processes such as SHG, DFWM, and SFG. which is the inverse of DFG. DFG is experimentally more challenging because you have to detect in the infrared, but we are confident that we can find and characterize this signal soon. And this is where we are currently at with our project. I'm looking forward to your questions.
In this poster, we'll speak about optoelectronic synapses based on hot electron-driven reactive tunnel junctions, which can be used as fundamental building blocks in future neuromorphic computing platforms, which utilize the principles of probably one of the most efficient computing systems in the world, our brain. Actually, computation in the neural networks of our brain happens not in the neurons themselves, but in connection between neurons called synapses, where the electrical signal is transferred into chemical one and then back to electrical in the receiving neuron. So the overall transfer of the electrical signal through the connection happens with a certain weight coefficient. Then, upon a learning process, these weight coefficients between various neurons are adjusted, so in the output of the neural system, it will be a result, resulting in an idea of an action of a living being. Now, how does this learning process work? How the weight coefficients are adjusted? Actually, in simple words, just using two rules. First, the weight coefficient can go up and can go down, and the second, that the weight coefficient depends on prehistory. It has a memory effect. It depends on how much signal has flown through the synapse before. So to realize an artificial synapse, we just need to create a system obeying these two learning rules. So here it will be our artificial synapse. One neuron will be a gold nanorod, another neuron will be an epileptic gallium-helium electrode, and a synaptic gap will be a tunneling gap between these two electrodes created by PLH polymer. This system can be created on the basis of nanorod metamaterial by depositing a polymer and then a second electrode. So, let us realize the rules. First rule will be realized on the basis that tunneling through the tunneling gap is very sensitive to whatever happens in the gap. So, we can change the weight coefficient for the tunneling by changing the state of PLH polymer by reducing it or by oxidizing it. So in this way we can adjust the weight coefficient for tunneling, but not only for the tunneling, because some of the electrons tunnel inelastically, creating light, so we can adjust weight coefficient for the light emission as well. And actually, that's what we observed in this experiment. We put our system in reducing or oxidizing atmosphere, and we saw that we changed the weight coefficient for the light emission, and so it is weight coefficient for the tunneling as well, because these two things are related. Now, what about the second rule, about memory effect? The thing is that this reaction is critically catalyzed by hot electrons created by elastic tunneling. So, the state of the reaction, it depends on how many hot electrons has been in this region before, or in other words, how much tunneling current has traveled through the tunnel junction before. So this is the memory effect, which we need to realize. Here it is. And this effect we can see on these graphs when the emissive state and resistive state depends on how many hot electrons appeared on the other side before. Finally, hot electrons can be created by illumination of light as well, which gives our synapse the true functionality of complete optoelectronic synapse. So for details, see my poster or these references. Thank you for your attention.
In this poster, we present our work on refractory nanoplasmonic materials, where we compare the temperature stability of individual titanium nitride and gold nanodiscs in order to assess their suitability for use in high-temperature plasmonic applications. We fabricated discs of titanium nitride and gold with varying diameter using electron beam lithography, and then assessed their cathode luminescence response, where we excite with an electron beam and collect the radiation that is emitted into the far field. And this allows us to observe excited plasmon modes within the discs. We can then identify these modes using simulations, and we see here that the dominant mode in the visible spectral range for both titanium nitride and gold is an out-of-plane dipole mode. We also see that titanium nitride has peaks that are lower energy and broader when compared to gold, and this agrees with the data that we collected experimentally. We also note the evolution of higher order modes as disk size increases, and we can observe this as well in the gold nanodiscs of 350 nanometer diameter. So after we characterize the properties of room temperature, titanium nitride and gold discs, we completed an annealing study to assess their temperature stability and to observe any changes in the cathodoluminescence response or the morphology. So in the annealing study, we heated samples for 30 minutes at a time at increasing temperatures from 100 degrees. And after each anneal, we measured the cathodoluminescence response and assessed whether there were any changes in the morphology of the film using SEM. And we see that there's different degradation mechanisms for the titanium nitride and the gold discs. The gold discs display changes in their shape from 300 degrees, whereas the titanium nitride retain their shape up to temperatures as high as 600 degrees. However, there are spectral changes in both gold and titanium nitride from 200 degrees. So this indicates that there's a different degradation mechanism for titanium nitride, and we believe this is due to oxidation of the titanium nitride with annealing. We simulated this oxidation using a core shell structure, where we increased the amount of oxygen in a thin titanium oxynitride layer coating a titanium nitride core. And we observe redshifting and lowering of intensity of the cathodoluminescence response, which is what we see in the annealing study. So we can conclude that titanium nitride and gold have comparable temperature stability when patterned on the nanoscale when considering their optical response, but titanium nitride may perform better if encapsulated with an oxidation barrier. Thank you.
Okay, so I think this concludes our poster session, and it also includes the morning session. So thanks to all of our speakers who have summarized some of the highlights of our progress, and thanks mainly to all of you who have stuck around for the whole morning.